Okay, let's go ahead and get started. A lot to get through today, so let's just jump right in. Question of the day. This one surprised me. I didn't realize Chrome was so popular. I'm still a Firefox user, I guess, old-fashioned. I wanted to do something. So last time, any of you who watched the lecture from Monday know that I screwed up at the end, that I meant to be showing you the execution of this program, and instead I was talking about it, but not actually showing it. I just wanted to run it quickly so to kind of show you, so that you could see it, So I did 1,500 numbers for algorithm 1. That was the n-cubed algorithm. So what I was predicting, as an experiment, is that doubling would lead to 2 cubed or 8 times as much time, and that tripling would lead to 3 cubed or 27. So 8 and 27 were the predictions that I was making about how the results that this program would produce in this case. 8 and 27, not too bad. And then when I ran it on 30,000 numbers for the middle algorithm, which was the n-squared algorithm, I was predicting 4 and 9 as the ratios of the amount of time taken to run the algorithm. 4 and 9, not too bad in terms of me using the computer science to predict. And with the 50, 1, 2, 3, 1, 2, 3, with the 50 million things using algorithm 3, I was predicting that we would get 2 and 3. It runs so fast it's hard to get a very good read on it. But 2 and 3 would be what I was predicting for the linear one, and we get 2 and a 3. Pretty good, actually. So anyway, that was from last time. This time, so let me just kind of jump in with what we're going to be doing for today. So we've been talking about various ADTs. So we've talked about lists and sets and stacks and queues. Those are all abstract data types that we've talked about. Today we're going to talk about what are known as maps, which is kind of the last major ADT that we're going to be talking about. And we'll be practicing it in the next homework assignment. Map is kind of an unfortunate term, because when I think of a map, I think of something that I can use to tell me how to drive downtown or something, But this is more a mathematical notion of map. So they're thinking of something like a function, y equals f of x. And the mathematicians, when you have a function like that, the terminology they'll use is that the value of x is being mapped into some value of y. Given an x, I can give you a y, that it maps to. So that's kind of where that terminology comes from. Other terms that are used for this: dictionary, actually, because you look things up in a dictionary, you look up words and you find their definition. I'm not a big fan of that, but anyway, it's another term that's used for this sometimes. Associative array, and I'm going to remind you about that, particularly in the second example we're going to look at. It's a more technical term, but it's an interesting extra terminology for what a map is. So what do maps involve? They involve key value pairs. So we saw that we dealt with things like array, list. I should use the interface. List of E, for E was short for element type. In the case of maps, if you look up the internal Java documentation for it, you'll find that it's map of k comma v. So there are two things that are inside of the less than, greater than, two types, and those types represent keys and values. So a map is basically a set of key value pairs. Given this key, this is the value that goes with it. Given this key, that's the value that goes with it. I kind of wish that when Java indicates this, it would show you something like key being mapped into a value, kind of like this: given an x, we get a y with an arrow. What they tend to do, like if you print a map, we're going to do that today. When you print a map, it shows the key value pairs with a key and then equals value. So they use an equals sign to kind of show you the separation between the key and the value. I wish it was an arrow, but you can imagine that it's like an arrow. What I would say is probably the most familiar thing for you for this would be the way that databases are used. Because I think you're probably used to database keys. You know, if you are going to contact the registrar about some issue with your registration or paying your tuition, or you're connecting with some office on campus, and they want to talk to you about something, they'll tend to say, give me your, I usually ask the audience, what do they ask for? They ask for your student number, right? So they use the student number to look you up, to kind of see your records. So the student number is a key. So they're using that as a key. Databases have keys that are used to look up entries in the database. And so given your student number, I can find a report of what courses you're registered for, or I can find out about your dorm assignment or whatever. So, the key is used to look up the data, the value. So that's key value, is kind of what we do there. We're also used to social security numbers being used in this way. Given your social security number, we'll look up your entry in the database. So that's a lot like of what a map is like. I have put together a list of common math methods. So we did this when we did lists and sets, as I showed you kind of this list. This is going to be in the notes for today in case you're interested. It'll also be on the class webpage tomorrow. You're going to be doing this in section, and this will be included in the section cheat sheet. So you'll have a copy of that on the class webpage tomorrow to be looking at when you go to do the section problems. So this is a subset. I mean, you can look at the online documentation and see all of the things that are part of the map interface, but these are kind of the main ones that we're going to use, and we're not even going to use all of these, but this kind of gives you a list of the most common things that we use. And this little sample program I have here is using the put command, and that's what's used to set up one of these key value associations. You give it a key and a value. So I just have a little short program here that's using a map that maps strings to strings. The name of a class is mapped to the name of the instructor. So that's kind of what I'm doing here. Tree map is the implementation we'll be using for now. We'll see another one later, but this is the one I'm going to have you use for now. Tree map has the property that it puts entries in order by the key. So here the keys are course names, and so it's going to alphabetize the course names. There'll be an alphabetical order in the map because that's kind of what a tree map does. But the idea is that I keep track of the fact that 143A is being taught by Stuart Regis, 143 by Stuart Regis. These are just some of the courses that are 100-level courses that are being offered this quarter. And so I set up a little map for it. And I mentioned to you, if we compile and run this, notice that it ends by printing the map. And let's take a look. You can see there's the key CSE 142 is associated with the value Mia Natsuhara. So CSE 143A key is associated with the value Stuart Regis. So you can kind of see those key value pairs there when you print out a map. It just shows you a long list of them. Notice that you can have a repeated value, so you can have two keys that map to the same value. I mean, I'm teaching two different courses, so I can be listed as the instructor for two. That's not true of kind of the duplicate keys. So there can only be one mapping for a given key. It's like a function, right? With a function, there's kind of a unique answer. Given an X, there's a Y. And the map is like that. Given any key, there's only one answer. You can't have more than one answer. Now, you can do a put command where you give it a key you've given it before. So if you do that, if you do a put command where you have a key that's already in the map, then the new association overwrites the old one. In our second example, we're going to actually make use of that. That's what we're going to want it to do, is to replace the old association with a new association. So it'll only keep track of one value associated with a given key. So the keys are unique in that sense. There won't be two entries for CSE 143A. If you had co-instructors or something, you'd have to do something like including both of their names as part of the value or something. So anyway, the keys, only one entry for a given key. All right, normally I'd ask for questions, but we don't have the opportunity to have questions. So let me show you a problem that I want to work on with you. So I've put in some little starter code here that asks for the name of a file, and it reads in the words of the file one at a time. The first thing I wanted to do with this is not using a map. I just kind of wanted to do something we've already seen before. What if I wanted to take a file like the novel Moby Dick? So I have that as a text file that I can examine. Moby Dick has over 200,000 words. It's a big novel, lots of words. But how many unique words? So if you wanted to figure out the unique words, how would we do that? Well, and normally I get someone who recognizes that's what sets are good for, because remember, sets eliminate duplicates. So I could have a set of string, suppose I call it count, which is a new tree set, and then we can use the diamond operator on the right-hand side. And then to process a next word, we could just say count.add that next word into the set. And then after the loop, we could say system.out.println size is equal to count.size. We can ask the set how big it is. So let's go ahead and compile, and you'll see a little more. We can scooch it up a bit. And I'll say moby.txt is what I want it to use. And it finds that there's 32,000 unique words. So over 200,000 words, but only 32,000 when you get rid of duplicates. Now, doing it this way, this is going to end up making if I had like the word whale, that appeared in Moby Dick, it does appear in Moby Dick, versus say the word whale with a capital W or whale in all uppercase letters, those would be considered different words because it is case sensitive in what it's doing. So I'm going to try to make it a little better than this by saying to lowercase. So I'm kind of happy to just have everything be lowercase, and then these different versions of whale collapse into the same word. It's not going to deal with things like what if it has a period after it or something. So anyway, we could try to do something more if we wanted to, but it's a pretty good answer. I don't know if you have a guess. We had 32,000 words when we didn't deal with this. You could make a guess about how many words it's going to have now. It ends up with 30,000 words, 30,368. So a little lower, a couple thousand lower when we turn everything to lowercase. All right, so that's something we've already seen, a set, that would kind of eliminate the duplicates. But I want to do a map. And so what I'm interested in doing here is not just one count, of kind of the number of unique words. I want to have a count for each individual word. So like for the word whale, I want to know how many times that occurs in the file. How many occurrences are there of whale? Well, we know there are 30,368 different words. And so in a way, what I want is 30,368 counters, right? A counter for each word. So how do we do that? Well, today's the lecture on maps, so pretty clear that we're going to be doing a map. And we're trying to keep track of a count for each word. So given a word, we'll use the word, the string, as the way to look up the count, and then we'll associate it. I mean, we could say we'd associate it with an int. That would be kind of the right idea. But remember, we can't use int. We have to say integer. So, but we'll think of it as being int. We'll treat it as if it was being associated with an int. So I'm going to have my variable count now be a map. And let's make a new tree map, and we can use the diamond operator on the right-hand side. So we're not going to be doing this anymore. That was what we did with a set. With a map, we use the put command, right? That's how we put things into a map. So what would we do here? Well, this one is a little trickier because we're going to be associating words with different counts. But let's think about what we would do the very first time you encounter a word. So the very first time, say, we come across the word whale, what would we want to be doing? Well, we'd want to tell our map to have an entry for that next word that gives it a count of 1. That would be the initial count, right? The very first time we see it, we give it a count of 1. Otherwise, it's not in the map. So, the first time we see a word, we'd have to give it a count of 1. I'm going to go ahead and compile and run this version just to kind of show you, because the map has a size command as well. The map's size command tells you how many key value pairs there are. Now, we should get the same number because, as I said, we're trying to get a different count for each unique word. Let's go ahead and run it and we'll see. So we'll give it Moby Dick again. And again, we get a count of 30,368. So that's good. But now what I'm doing here is that when I encounter the word whale, I tell the map, that I want it to have an entry, whale has a count of 1. And then when I encounter whale a second time, I tell the map, I want whale to have a count of 1. And then when I encounter whale a third time, I say I want whale to have a count of 1. So over and over again, I'm telling the map to have a given word have a count of 1. And that's not what I want it to do, but that's kind of what it's doing right now. And so it's like it's overwriting the count, but it's overwriting it with the same value. It keeps replacing 1 with 1. So every one of these words is going to have a count of 1 in this version of it, because we kind of haven't done the right thing for what to do when something is already in the map. I mentioned before the idea that another term for maps is an associative array. And it's not a bad way of thinking of things to think of this map called count in using an array style notation. That that what we're manipulating is count bracket next. Now in an array case, that has to be an integer index. But here it's a string. But it kind of makes sense. We're looking up the entry in this structure for this particular word, the count of next. And what are we doing in this case? We're setting it to be a count of 1. So this is as if we had said, if we could use array style notation, the equivalent line of code would be that count of next is assigned to 1. In C#, that is how you would write the code. So in C#, the language allows you to be able to use the array style notation for maps, which is nice. But Java, the designers of Java decided they didn't want to go that route. Well, what do we want to do if it's already in there? Well, if it's already in there, what do we want to do the equivalent of? If we could use array style notation, what would we say? Like, if we've seen 18 occurrences of the word whale, then 18 is in the map. And what do we want to do? Well, we'd want to increment it, right? We'd want to have it go up to 19. We want to bump it up by 1. So we kind of want to do the equivalent of count bracket next plus plus. Well, as I said, Java doesn't let you do that. You have to think kind of about, in more detail, what does this mean to say count of next plus plus? Doesn't it say take the old count of next, add 1 to it to make a new count? So kind of compute what count of next plus 1 is, and then make that the new value of count of next. This would be an equivalent line of code using array style notation. Well, again, we can't use array style notation, but we can kind of translate using the map commands. So we know that put is the way to assign something into the map, to put a key value pair into the map. And get is the way to get the current mapping. Kind of, it's like looking something up in a list as well. But here we use the key as the way to say, tell me what that key is mapped to currently. So let's try to translate this. Count of next plus 1. How do we get the equivalent of count of next plus 1? Well, we need to look up the count for next, which would be count.get of next. So we use the get method to get the current count. We would add 1 to it, and then that's the new count. That's what we want to have become the new count. How do we reassign? How do we make that the new value of count? Well, we use the put command. That we say, I want next now to be associated with whatever this expression produces. So I want you to figure out what count.get of next plus 1 is equal to. So if it had been this, like if there was 18 occurrences of whale, we compute a 19, and then we make that the new association. And remember, that overwrites the old one. so that the 18 would go away and we'd remember that whale has a count of 19. And then kind of we come back around again, we would do count.get of next, we'd get a 19, we'd add 1 to it and get a 20, and say now have next whale associated with a count of 20. So it kind of goes up by 1 every time. So that's kind of translating the equivalent here. But now, and this is something that's going to be very common with map style coding, is that you often have to do something different the first time you encounter a key versus when you encounter it again. So we want to kind of do this the very first time we encounter a word, and we want to do this for the later occurrences of a word. So we need some kind of an if-else structure. Oops, I'll leave that comment in that has the array style code. I'm going to say if something or other, then I want to do these 2 lines of code, and else I'm going to want, well, that's not, that's just a comment. Else what I'd want to do is this line of code. So I'm going to do one or the other depending upon whether that key has been seen before. Well, again, this list of methods here for the map, there's a method called contains key that tells you whether something is in, a key is in the map or not. So I could say if count.contains key next. So if it's in there, then do this, and otherwise do that. Well, I think you can see we want it the other way, that if it doesn't contain it, we want to do that. So we could do equals false, and then we'd lose a style point for Booleans n, or we could switch around what's in the one or the other, or we could just use negation if we know how to use Boolean expressions well. So if it doesn't contain the key, then we put it into the map with a count of 1, and otherwise we get its old count, add 1, and make that a new count. So that's kind of the way we would do it using contains key. Let me mention, by the way, what I like about this particular example, this word counting example, is it has all the things that I want you to use for a map in the next homework assignment. So it's they're all listed here as well, but there's more here than you need. And so I can just kind of tell you that this is plenty, that if you understand the different map methods we've used here, that's enough to know what you need to do for the next homework assignment. All right, well, this would get us our different counters, but then we kind of want to see what they are. So then how do we kind of print out what's in the map? Well, there's different ways of approaching it. What we tend to do is to call a method known as keySet. So keySet returns a set of all the keys in the map. And these keys are all words, so they're all strings. And if I wanted to, traverse a set of strings, I can use a for each loop. So I can say for all of the strings, and I need a variable name here, how about if I call it word? All of the strings that I'll call word that are in count.keySet. So I ask the count, the map, to give me access to its key set, and I'm going to have a for each loop that goes over that key set. And I'm going to do a system.out.println of count.get of word. So I'm going to kind of print its count, and then a tab character, and then the word itself. So we'll kind of print a count and a word to see kind of what those different counts are. Now, if I do this for Moby Dick, it's going to have 30,000 lines of output. Here's something we can do that's a little bit fun. This program was called WED, right? wed.java. How about if we have this program look at itself and kind of count the occurrences of words that are in the program itself? And it ends up finding that there's 2 occurrences of scanner, 2 occurrences of public, and so forth, 4 occurrences of new. So it's kind of going through all the different things that are in the program and showing us a count for each of those different things. I have a version of it. So the one that I'm going to post to the calendar for today does something a little extra. So if I run this version and I use Moby Dick, it asks me for a minimum number of occurrences. So suppose I say that I only want to see things that occur at least 500 times. So then I don't get huge amounts of output. In fact, the word whale just makes the cut. There's 500 occurrences of whale. And these are other words that occurred 500 or more times in Moby Dick. So that'll be the version that I post to the calendar for today, is one that asks you for a minimum number of words as well. Okay, so that's a good example to understand. And this is a good example to understand for what I would describe as a simple map, where we're mapping from one kind of object to another kind of object. We're going to be looking at something that involves what I would call a nested structure, where we're going to map from something to something that is itself a structure. So the thing we map to is going to be a structure. So structures within structures, and that's why we kind of refer to them as nested structures. And I think that the hard part is the nested structures. So TAs will go over this in section tomorrow, and they'll try to make sure that you're up to speed on kind of the simpler versions like we did in this word count program. And then they'll spend at least a little bit of time talking about the nested. But I think that, that we don't have time to do everything. So that's going to be the thing I think you're going to find challenging for the homework. And so I'm going to start an example today where, it looks like we've got about half the time left. And I'm going to continue that example into Friday. So we're going to spend a lot of time on this example program. I designed it as a medium hint for the programming assignment. So it's a really useful thing to understand, an important thing to understand in order to be able to approach the homework assignment. And it's going to involve one of these nested structures. So it involves keeping track of friendship relationships. Oops, that's not what I wanted to do. I wanted to take a look at what I had here. I have a little graph here that shows various friendship kind of relationships. Let me show you the file that was used to generate that graph. So this file said that Ashley and Christopher are connected. So over here in the graph that was produced, Ashley and Christopher have a link between them. That's a friendship link. And friendships go in both directions. So if I say that Ashley Christopher, I'm saying that Ashley has a friend named Christopher and Christopher has a friend named Ashley. It goes in both directions. So there's a bunch of links here. And what I'm interested in is thinking about friends of friends of friends, kind of extended friendship relationships. There's a concept that came out of psychology, what's sometimes called 6 degrees of separation, the idea that on average the number of links between two people would be around 6. And there's interesting actual research that shows that this estimate that people made way back in the 60s is actually pretty accurate. I'll include a link to a talk by a fellow named Yuri Leskovic that he gave here, where he studied Microsoft data of who was chatting with whom throughout the world. He had a gigantic graph that he was working with. And he found it was kind of on average around 6. I think maybe he said it was closer to 5, but the number of connections. And obviously people can be very far apart or not connected at all. But on average, I think is where that came out. But let me show you. So let me show you how this program is going to behave when we're done with it. So let's scooch up this, and let me go to the Friends program, which is here, and let me go ahead and run it. And so I'm going to say starting at Ashley and going to Stuart. So what does this program find? So starting with Ashley, it finds that she has 4 friends: Christopher, Emily, Jessica, and Joshua. And you can see that here. Ashley has 4 different connections. There's Christopher, there's Emily, there's Joshua, and Jessica. She has 4 friends. None of them are me. But then those friends have friends. And so if it goes one more link, it finds Andrew, Jacob, Michael, and Sarah. That's still not me, but it gets to some other places. So from Ashley, it got to Christopher being 1 away. And the thing that's going to work, I think you can see, is that Jacob is 2 away from Ashley. And then and I'm 1 away from Jacob. So it kind of finds me 3 away from Ashley. And it says that we have a distance of 3. So and we're going to spend a lot of time in Friday's lecture writing the code that makes all of that work. The part that I want to talk about today is the underlying structure that we're going to use and how to read in this file, how to construct that structure that we're going to use. And it's going to be a map, so that's not terribly surprising. And I usually ask the class for what would be a useful way, what kind of structure would we want? What do we want to store in order to be able to solve a problem like this? And there's lots of answers you could give. I mean, a really obvious answer is that you could just store the pairs. You know, Ashley, Christopher, Ashley, Emily, Ashley, Joshua. You know, the links. I mean, certainly that would work. I don't think that's the convenient thing to have here. And I kind of point people to this as a clue, you know, to think about what I ended up deciding would be a convenient way to store this. So starting with Ashley, we wanted to be able to know who her friends are. So the structure that I want us to have is a map that takes the name of a person, like Ashley, and it looks up her friends. So it finds that Ashley's friends are these 4 people right here. That's why it's going to be a structure, because Ashley potentially has more than one friend. I have only one friend, but Ashley has 4. So that's why this map is going to map to something that is itself a structure. So given Ashley's name, we're going to want to get this set of the 4 friends. So what do we want to do? I kind of gave it away there. But how do we want to store this? I get lots of interesting answers. Some people say an array of friends. Some people say a list of friends. But let me ask you about friends. Can you, like if Christopher's a friend of Ashley, can Christopher be a friend more than once? And the answer is no, not in this way of thinking of things. You know, there's just one friendship between Ashley and Christopher, so we don't have duplicates. And is there an order to it? Do we have, is Christopher Ashley's very bestest friend? And in a Facebook type thing, no, we don't keep track of that. I mean, maybe there really are, friends who are better friends of Ashley, but our structure is not going to keep track of that. So what we want to have here for these 4 different friends of Ashley is a set. So we want to have a map that maps Ashley's name to a set that has the names of her friends. So the structure that I want us to create is something that so like here's Ashley's name. Given Ashley's name as a key, what it's going to map to, when we look it up in our map, is we're going to get this set of 4 friends. And so we want to figure out how to take that input file and build this map structure here. There are 21 names. Oh, let me also, I should have said this before, but I am vastly oversimplifying here. I'm assuming that if you use Ashley as the name, that there's only one Ashley in the world. Obviously you have to do something better if there's going to be more than one Ashley that we wanted to keep track of. We can't just use Ashley as the way to keep track of them if there's more than one. So I'm assuming that this is a simple case, small set of names where there are no duplicates. And if you had to have a duplicate, you might have like Michael G or Michael T or something like that. So we're assuming they're all unique. There are 21 different names that are used in this file. So one of the questions that I'll ask the class is, how many objects are we going to end up constructing? And 21's not a bad answer because we want 21 sets. For each person, we're going to want to have a set of their friends. So that's 21 objects we're going to construct. But there's a 22nd object, which is the map itself. So the map is an object we're going to construct that keeps track of all of this. And the other 21 objects are all going to, in a sense, be inside the map or referenced through the map. So 22 objects total, a map, and 21 sets, for the different entries in that map. 21 entries in that map. All right, well, I've got some starter code for us here that I want us to work on. I didn't fill in the type here. What's going to be the type? It's a map, and we're using people's names to look things up. So it's a string. We're looking up, say, Ashley, to find Ashley's friends. And what does it map to? I said that it maps to a set of string. So, who are Ashley's friends? We need a greater than here that matches this less than right here, but we need another greater than here to match the less than that was here. Welcome to nested structures. It's a little bit more complicated than it would be otherwise. I'm going to make a copy of that type because I'm going to use that in several places. So it calls a little method here, read file. So read file is going to have a local variable of that type. And we can use, on the right-hand side, we're going to want to make a new tree map. We can use the diamond operator so that we don't have to worry about filling in the details there. That's a nice application of the diamond operator. It'll know what to do because of what it had on the left-hand side there. And so this is going through, and it's reading various lines. Remember what that input file looks like. It has lines of input like this. By the way, what I was showing you here is a little program called GraphViz that drew this graph for me. It's a cute little program, and it's available for free on the web. So I'll include that on the calendar today, too, in case you want to write your own little files like this, or you want to make a, this is the input that GraphViz used. So now we're writing something that wants to look at the same input file. And so if it sees a line like this that has a dash dash in it, so it ends up seeing a line that has a dash dash, then it pulls apart the line into a name 1 and a name 2. It has to skip the dash dash, and now it wants to process those two names. Well, one of the things that I think is not obvious, maybe I'll ask this as a question. So think about it. Initially, the map is empty. There's nothing in it. What should be true of the map after we process this first line of the input file? How many entries should be in the map after we've processed the first line of the input file? And people sometimes say 1, but that's not the right answer. The right answer is that we want 2 entries. We're going to want to have the map remember that Ashley has a friend named Christopher, and we're going to want it to remember that Christopher has a friend named Ashley. Remember, friendships go in both directions. So we're going to want to record something, basically 2 different bits of information. So I'm going to do that by having an extra method that I can call twice. So I'm going to say add to the friends map something where you have name 1 followed by name 2, where say it's Ashley followed by Christopher, and then add to the friends structure in the other order, recording the fact that Christopher is a friend of Ashley. So we're going to want to switch the order of the 2 names. So it records both directions, two different things to record. So then we're going to want to have a public static void add to method that takes our friends structure, and it also takes a string name 1 and a string name 2. One of the rules when you break a line is that you can line things up like this inside of the parentheses. So let's kind of come back over to here, and we'll have my closed curly brace, so I'm ready for that. This add to method is very important for you to understand, and I'm glad we have a big chunk of time to talk about it. And I'll talk about it even more at the beginning of Friday's lecture. So, I said this program, the Friends of Friend program, is meant to be a medium hint for the homework. Some parts of this program are a little bit complicated, kind of not all that helpful for the homework, and those parts I'm going to spend less time on. I'm going to go really slowly through the parts that are most relevant to your homework assignment, because I really want to make sure that you understand how this relates to your homework. And this is not easy stuff. Kind of getting used to working with a nested structure takes a while. So it's appropriate for us to kind of do this slowly and make sure that we understand what's going on. Now, when I have a live audience, what I sometimes do, I've mentioned the idea that it can be useful when you're dealing with various kinds of objects to anthropomorphize them, to turn them into people. And so I'll ask for several volunteers who agree to be objects of this program, agree to be objectified. Well, I got no one in the room, so I got nobody to volunteer to be an object. So I'm going to do something else instead, which is I'm going to have a little file here where I'm going to keep track of all of the different objects that we construct and how we can refer to them. Remember that by the time we're done, we're going to have 22 objects. There's going to be the map and the 21 sets of friends. If we went all the way, we're going to just get started. We're only going to look at the initial things, not the whole thing. Well, Objects. What have we done so far? We've done one call on new, and that was up here. We constructed the map. So let me say in here that our map is an object that we have already constructed, and we refer to it as friends. That's what we're using that variable friends for, is to keep track of our map. Okay, so let's see what we want to do here in the code. So suppose that, it's Ashley and Christopher. Now, tell me this. We've constructed the map, but is there anything in the map? I mean, how do things end up in the map? You call put. Have we called put? Let me take a look at the lines of code. We haven't called put. So the map is empty. It has a size of 0. There's nothing in the map. Now, in order to kind of record the fact that Ashley has a friend named Christopher, we're going to want to have an entry in the map for Ashley, and we're going to want that entry to say that Ashley is associated with a particular set of friends that includes Christopher. So I'm going to say the following. I'm going to say that we want a set of string that I'm going to call the friends. We're going to need to construct a set. There is no set right now that would keep track of Ashley's friends. So I'm going to say this is a new tree set. We can use the diamond operator. And now let me record the fact over here that set of Ashley's friends, is kind of something that we've set up. And we have this local variable called the friends that keeps track of that. Now, the friends is a local variable that's going to go away. So, if we want to remember this, we got to remember it in a different way. Well, and the way to remember it is that we want it to be in our map. We want Ashley's name to have an entry in the map that maps to this set that we just set up. So what I'm going to say here is that one of the things we need to do is to tell the map, the hey map, friends map, I want you to have an entry, I'm putting an entry into the map that associates Ashley's name with this set of friends. So that's one of the things that I need to do, is that I need to tell the map to have an association. Now, after I do this, the map has one thing in it. And the one thing is something that associates Ashley with a set of friends. What's in that set? The set is empty. So, because we haven't added anything to the set yet. But we've associated in the map Ashley's name with this set of friends. So, I said here that it's the local variable, the friends, but I'm actually going to change this because long term, we're not going to use that local variable. We're going to talk to our map. Once we do this call on put, once we say, I want you to associate Ashley's name with that set of friends, we're going to be able to ask the map, get me Ashley's friends. Because that's what the map does. The map remembers these associations between names and sets. So later, when we're going to want to look up who Ashley's friends are, we'll ask the map to give us a reference to the set. Now here, this call on get, remember, this is returning a reference to a structure. That's not returning a simple thing. That's returning a reference to a structure, a set. It's returning a reference to this object, the set of Ashley's friends. But now, as I said, we haven't told the set to have anything in it. The set itself is empty. So I'm going to say the friends.add. Remember, you add things to a set. And what do we want to add? We want to add Christopher. We want to add that, name 2. We're going to want to add name 2 over here. And then I'm going to add something here where I say system.out.println friends is equal to friends, to be able to see kind of what's in this structure. Let me set a little stop right here. So at the end of the first execution of the add to, we're going to have two objects. We're going to have our map, and we're going to have a set of Ashley's friends, and the map will have one entry in it that kind of associates Ashley's name with a set that has Christopher's name in it. Well, let's see if I compile. I may have forgotten something. Way up here in the read file, I didn't include the fact that that's returning a map of string, set of string. That's our friends structure that I had kind of left that to fill in. And what did I do here? It says equals read file public static map of string. what is it upset about for us? Greater than expected. Oh, I guess when I did the copying, I didn't quite copy it correctly. I must have missed one of those characters. Oh, and that's going to be true wherever I did that. So I meant to copy the whole thing, but well, we can just let the compiler find these things for us. And it's down here too. You guys may have noticed it when I was doing it. I didn't move my cursor to cover everything. Okay, let me do a debug, and let's take a look at what's going on here. And you can see that we've got Ashley Christopher. So that's name 1, name 2, Ashley Christopher. Here's our object called the friends. And now if it's done what it's supposed to have done, it should have added one entry to the map, which associates Ashley's name with her set of friends, and it should have put the one name into that set, which is Christopher. So let that line of code execute, and we see that there is the map, has the one entry, Ashley is associated with Christopher. I'm going to let it continue. So now what we do is we call add to in the other order. So it's going to be Christopher followed by Ashley. So when we go into the method, what we find now is that it's Christopher followed by Ashley. And if we let these different lines of code execute, the first thing it does is it creates a brand new set. So that's our third object, the set of Christopher's friends. Initially, the friends refers to it, but later on, we're going to do the same kind of thing where we would say friends.get of Christopher, if we want to be able to get Christopher's friends, is the reference we would use. And it tells the map about that association, and it adds Ashley's name to Christopher's set of friends. So now when I come here and I print, you can see that there's two entries in here. The entry for Ashley, who her set knows that Christopher is her friend, and there's an entry for Christopher that knows that Ashley is her friend. A total of 3 objects, the one map and the 2 sets. So that's kind of where we're at right now. Remember what I said is that if we did this very carefully all the way to the end, all 22 of the different objects would be listed here. But let's see what happens the next time. So let's let it kind of continue. So I'm going to let it come up to here, and it kind of comes back around, and it reads in another line of data, and it gets to a call on add to, and then I'm going to let it go in and do that call. Now this is dealing with the second line of the input file that has Ashley Emily. So for that second line of the input file, name 1 is Ashley, and name 2 is Emily. What's it about to do? It's about to construct a brand new set of Ashley's friends, because Ashley is name 1, right? It's about to make a brand new set that we'd use for keeping track of Ashley's friends. We already have a set for keeping track of Ashley's friends. If we construct a new one and tell the map to associate it with that one, then we lose the old association. We'd forget that she's friends with Christopher. So just like I said before, it's often the case that you do something different the second time you see something. So what are we going to, this is the second time we've come across Ashley's name. The second time that we see Ashley's name, what we're going to want to do is we still want to know about her friends, but we're going to ask the map to get us her friends. We're still going to want to tell the friends map to add name 2 to it. We'd want to have Emily's name added into it, but we want to do it with the existing set, not making a brand new one. So this is another one of those cases where, let me go ahead and end the debug, where we're going to want to have an if. We're going to want to say if something is not in the map, so if it's not the case that friends.contains key name 1, so if it's not in the set, then we're going to want to execute those 3 lines of code that create a set for that person. Otherwise, what we'd want to do is add that to the existing set. So that's kind of the key of what's going on here, is creating a brand new tree set to keep track of somebody's friends versus adding them to an existing set. We're about to run out of time. Let me see if I can debug. And the first time, remember, we get Ashley, Christopher, and then let me run again. The second time, we get Ashley, Christopher, and let me run it again. This third time with Ashley, Emily,